Okay, where limits fail to exist. So this is AP Calculus, AB. So we look for a limit. When we're looking for a limit, we have to keep in mind that a limit is a number that we're approaching. So we're kind of looking at it like this. We're saying the limit of f of x as x approaches c is equal to L, where L is a number. L is a number. I'm not describing that it's an integer or that it's a whole number or that it's an irrational number. I'm saying it is a number that can be reached. So let's start with that idea of a limit. So as x becomes arbitrarily close to this value c, does the height become close to this value that we're approaching? So we've talked about this in great detail. Now I want to talk about some ways where limits fail to exist. So here's a Cartesian plane right here. And I have this function, and the function looks like this. The function might look like this. And maybe it looks like this down here. And maybe this is y is -1 down here, and this is y is 1 up here. So imagine that there's this function, and this is what we're going to try to do. We're going to try to squeeze from both sides and see if we get to a height. So as we move in this direction and this direction simultaneously, we're looking for a height. You can see that our function is approaching two different heights. And this function could be a function like, I don't know, this could be f of x is equal to the absolute value of x over x. Well, if you think about it, as you approach from negative numbers, all the values will be -1, right? Because you're going to get a number over the opposite of itself on the left-hand side, so it's going to always be approaching -1. From the right-hand side, though, it's always going to be approaching 1. So this limit fails to exist. Why? Because this value L is has to be a single value, and this one is approaching two different values. In this case, it's approaching a value of 1 and a value of -1. All right? So that's the first way that a limit can fail to exist. Another way that a limit could fail to exist is by not really approaching a number L, and it could look like this. So here's our Cartesian plane again. So here's our Cartesian plane. And maybe we have this function that does this. Maybe our function does this. Maybe our function goes here, and it presses and presses and presses and presses, and it becomes asymptotic to the y-axis. And then on this side, maybe it does exactly the opposite thing. So if you can see, so let me define this function a little bit, give it a definition. Let this function be f of x is equal to 1 over x squared. As x gets arbitrarily close to 0, we can see this thing just grows and grows and grows and grows. However, these two pieces of the curve will never touch. They're never going to meet. So if they were doing this, maybe they're going to do this and here. Say, well, there's that value that they're going to approach. But that's not what's happening here. These numbers are becoming infinitely high as x becomes closer and closer to 0 from either side. So why does the limit fail to exist here? Because this is considered unbounded behavior. And unbounded behavior is exactly what it means. It doesn't really have a good boundary. So unbounded behavior. Where the first example that we saw was because the function was approaching two different L values. Here, it's not approaching any L value. It's just, in this case, it's becoming infinitely high. The behavior is unbounded. So the second case is unbounded behavior. Let's look at the third and final case for where limits fail to exist, and I think we'll have a good working definition of this. The third one is this oscillating behavior. So it might look like this. The function may be, the function may be smooth and well behaved down here. So it may look something like this. It may drift in here like this, and it might dip down. But then what happens is it starts to act very erratically. And then maybe the behavior becomes normal again and drifts off like this. So what could this function be? This could be, I don't know, maybe f of x is equal to 1 over sine x. And what's happening here is that this function let this be +1 up here and let this be -1 down here. The height of the graph is changing so quickly you know what, if I could squeeze this together from both sides, and like if I was, looks like I was compressing a spring from the left and right hand side. Right now it looks a little bit stretched out. If I could press this thing in together, you could see that this thing, the graph is oscillating like crazy. So the limit doesn't exist, because no matter how small the area you look at, the heights are going to be switching from 1 to -1, 1 to -1 so quickly that we can't get a good limit, right? We're looking for this one single L value. So that gives us our three cases. The first case, behavior that differs from the right side to the left side, that was the f of x is the absolute value of x over x function. The second one was unbounded behavior, and we used f of x is 1 over x squared, and we approached 0. And the last one we're looking at is 1 over sine of x, and we look at this behavior as x approaches 0, and this oscillation makes it impossible for us to see that. All right? So those are our three cases.